Oh yeah, wowee. This is gorgeous. Looky here. Holy cow. Look at these rip-up clasts. So it's kind of the opposite of what you expect. Oh man, that's creamy. It's a good way of going about life in general. Just be a clast. I always tell my students that. There are very few places on Earth you can walk on an ancient landscape on ancient landforms that are essentially the same as they were when they were originally deposited. I'm in just such a place south of the town of Green River in Utah, and I'm standing on a Cretaceous channel body that's in the same geometry, same shape as the day it was deposited, filled in, and abandoned by the fluvial system that left it. How is that possible, and what does it look like, and what can we learn from it? Those are just some of the questions we're going to tackle on today's episode of the Rock-o-Rama. As always, let's get some context on these outcrops, because before you dive into any set of rocks, you really want to know where and when they were deposited, because that's going to help inform your interpretations of them. We are in what's called the Ruby Ranch member of the Cedar Mountain Formation, which is an earliest Cretaceous rock unit, unique in the western US because it captures a time that's missing throughout most of the region. If you went to Wyoming, Montana, Colorado, or any of the southwestern states, and even in the east, this interval of time is not represented because there was a giant regional unconformity, meaning there was erosion happening in North America during the early Cretaceous, and sediment was being stripped away, just like what's happening in North America today. Today, all the sediment is largely getting dumped into the Mississippi River Valley. Back in the Cretaceous, it was getting dumped into what's called the McMurray Insides Valley system, which was flowing to the north instead of to the south, and it was emptying into the Arctic Ocean instead of the Gulf of Mexico. So if sediment was getting stripped away throughout North America, why is this unique little part of northeastern Utah special? Why is there Cretaceous sediment being preserved here? Well, to answer that, we have to go back a little bit further in time and take a quick side trip to Moab to look at what's going on down there. There are some beautifully exposed examples of salt walls, salt domes, salt diapirs, which is what happens when layers of sediment pile up on top of thick layers of salt. The salt starts to move around and squish upward, almost like you're stepping on a tube of toothpaste with the cap off of it. That salt movement creates little mini basins between the salt domes and walls, and in those little mini basins, sediment gets trapped. I did a brief video on this topic about a year or two ago, and you can take a look at it here in case you get curious. But for now, all we need to focus on is the fact that with a lot of salt movement in an area, you tend to create little pockets where sediment can be preserved, even when it's being stripped away in other parts of the region. So during the early Cretaceous, here in northeastern Utah, there was still enough salt movement, just enough, to create little pockets of preferential preservation for the early Cretaceous sediments that were moving through. And that's why we have it preserved here. Now, in terms of what kind of depositional environments we're talking about here, we've got fluvial systems, big, broad, distributive fluvial systems that are really kind of a continuation of the environments that existed during accumulation of the Jurassic and early Cretaceous Morrison Formation. Both the Morrison and the Cedar Mountain Formations in this part of the world contain mostly a combination of clay stones and siltstones representing the distalmost parts of the fan systems, and some little sandy and gravelly channel bodies which represent the little threaded channels that came towing out into the distal part of the fan as that system kind of whipped back and forth. In this case, the channels were pretty avulsive. In other words, they were cutting, filling, and then jumping somewhere else during the next cut and fill episode. So they didn't stay still long enough to create big sheet-like bodies of sandstone. Instead, they made these really discrete little channels that look a lot like an active modern fluvial channel. And that's what you can see so clearly in the Google Earth images. As a sedimentary geologist, I and people in this field are used to looking at two-dimensional cross-sections of sedimentary bodies that are preserved in the rock record. And it's usually afforded by either a river cutting through and leaving a cliff, or a road cut. We love our road cuts. Or something like that. The famous Book Cliffs, which is just to the north of me up that way, is a spectacular example of a naturally occurring cliff face that you can follow for miles and miles and follow individual sand bodies that represent shore faces dipping out into the sea. The San Rafael Swell, which is just that way, due west of me, is another example of a natural tectonic uplift that has given us spectacular cliff faces and in some cases three-dimensional views of the outcrops. This is not that. This is actually a three-dimensionally preserved outcrop, so I can walk on the cross-sectional view and I can walk on the planform view and look down at the fluvial channel body. It's pretty impressive. And that's what we're going to do now, is kind of walk along and see what we see in this channel body. So the best place to start is at my feet. And immediately you recognize the really coarse-grained nature of this stuff. This is gravelly. This is a very coarse-grained channel. And for being such a small system, it's surprisingly coarse. That's telling us it's got fairly high energy concentrated in the flow. And these coarse-grained clasts are probably coming from the uplifted severe mountains to the west. So these streams were probably high intensity, high velocity, really rapid discharge, just gooshing conglomerates, gravels, and sands, and mixing them all together in these bed forms. So we're going to walk along and see what else we see. All right, take a look at this. This is a cross-sectional view of what we were just standing on, and it shows a really interesting succession of rock which captures flow events in the Cretaceous. So it starts off with that very coarse-grained gravel again, that conglomerate, and you can see where it's actually scoured into older sand. That is a super sharp contact. I mean, you can put your finger right on that contact. So here's an older sandy bed, then here's the conglomerate lag, and then just as abruptly on top of the conglomerate is another fine-grained sand. And that fine-grained sand is pretty well laminated. You don't really see too much in the way of ripples in it. It's pretty laminated. There might be a little bit of rippling up here. Looks like some ripples up here. So in terms of flow that produced this, we could say it's very high flow, almost debris flow, poorly organized, and then it got more organized as the flood waned. And these are the waning flood deposits of that depositional event where you had the little ripples and little laminated sands forming. So this could all just be one big flood event in the channel body. And that's about 3.5, 4 feet, so a little over a meter tall. And if we carry that across to the rest of the channel itself is only about maybe 3 or 4 meters thick. It's not a very deep channel, not a very thick channel. So we're looking at something that was maybe cut and filled pretty rapidly. That's just something to keep in mind as we keep looking at this. Here's some really interesting features. Look at that. What's happening is the lichen is growing on some of the finer grained material. So there's sand dipping down into some silty heterolithics, and the lichen is growing on the silty heterolithics, really accentuating those little sandy beds. That's pretty cool. All right, let's keep going. This is the uppermost surface of the channel body. As you can see, it's still very coarse-grained, and it's got that black coloration courtesy of the manganese oxide. That's very common out here in the Southwest. It's desert varnish, some people call it. And probably what happened here is this stuff is the remnant of mudstone or siltstone that had been sitting on top of the channel, and this manganese oxide percolated out of it and got absorbed by the porous sand, porous and permeable sand on the top of the channel. The mudstone of silt has since eroded, and we're left behind with this channel body. All right, look at this. We have some beautifully preserved three-dimensional trough crossbeds. So we're seeing the individual foresets of troughs, and they've got those broad arcuate shapes to them. And the axis, you can find the axis by looking up the smile, the center of the smile. It's going roughly that way, which unsurprisingly is the way the channel is flowing, was flowing in the Cretaceous. So these bed forms, these dunes, these subaqueous dunes, were building downstream. The coarseness is really surprising. I wasn't expecting it to be this coarse all the way throughout from bottom to top, especially in this uppermost part. There's still heavy-duty conglomerate. These are pebbles in the uppermost part of the channel. Yeah, and take a look at this. In amongst the pebbles, there are some really big whopper clasts. This looks like a well-cemented mudstone clast. Here's another one here, another one here. So this is ripping up. It could be limestone. You know what? Look at that surface texture. That's typical of a limestone. So these might be limestones. I forgot my acid to drop and see if it fizzes, but I will have to collect some and bring it back and drop some hydrochloric and see if it fizzes. Okay, so here's the more familiar cross-sectional view of a channel body. This is typically what we see in the sedimentary record, is a vertical succession cut lengthwise, not necessarily looking at the top. But in here, there's a lot of really interesting features that we can't see from the top because they're buried, but this gives us a cross-sectional view of the channel body and helps explain a little bit about how it filled in, what its process for development and abandonment were. This lowermost part of the channel is actually very fine-grained sand. And you can see it's cross-bedded, somewhat deformed. Might have had some dewatering. In other words, the whole thing just kind of, after it accumulated, some settling happened, some water came squirting out and it kind of settled back down. Or it might just be sigmoidal bedding. Now take a look at that. The basal scour has rip-up clasts. So that's the channel lag at the base of this channel probably. There's also what looks like some fine-grained, kind of greenish, maybe chlorite-rich, silty mudstone. That's probably from the overbank. And here's the cross-bedding. And looking at it closer, it doesn't look too terribly deformed. It looks pretty in place. And you can see there's small-scale ripples stacked on top of each other. There's some going that way. Some seem to be kind of maybe going that way. We're getting a cross-sectional view at an oblique angle. So I'm sure there's some spread in the ripples and it gives a kind of weird impression of which way they're going. It's not bidirectional. You're just seeing a different spread, but it's a fine-grained sand is the point. So we have conglomerate, then a fine-grained sand. Then on top of that, we're back into some conglomeratic sand, fine-grained conglomeratic, and the top cap is all conglomeratic. So it's kind of the opposite of what you expect in a normal fluvial channel deposit, where the coarsest material is usually considered to be at the very base of the channel, and the finest grain material is supposed to be at the top. This is doing the opposite. So we've got very fine grain, at least at this spot on the channel body. We've got fine grain at the bottom, and coarser grained at the top. So let's keep walking along, see if this trend holds up or if anything changes. Holy cow! Look at these rip-up clasts. These are huge rip-up clasts of limestone. Looks like limestone. Now I'm thinking this limestone originated as carbonate nodules in the soil surrounding the channels, and it's a type of carbonate called caliche that forms in mature, dry soils. Wow, look at this one. This is enormous. That's almost a meter in diameter. So this is a big, big concretion, or clast of limestone. So we've got huge chunks of limestone tumbled in with the gravel. That's high energy. That is a super high energy flood that deposited this sediment in this channel body, this upper part of the body. So again, this is the upper part. The lower part has got some finer grained as well as conglomeratic material in it. But wow, that is some energy. It looks like this higher energy facies, which is that dark conglomeratic material, pretty much continues along the entire cliff face. But what I'm interested in is that kind of finer grained appearing, lighter material that sits on top of it. And there's a knob of it right over here. So I'm gonna walk on top of this channel body, follow it along and see what that lighter color material is. That might shed some light on what kind of channel body this was. As I'm walking along the surface here, I'm struck by the fact that it's really fine-grained material that I'm walking on. So the top of the channel body is that dark layer right in front of us. But what I'm walking on now is very loose sand, silty almost. I know it's weathered and eroded, but it looks like some of it might be in place here. And it does look like it's maybe finer grain. In fact, there's some over there, some sand. So I think we might be out of the channel in the floodplain on top of that channel body. So we'll take a look at these sands. That will maybe give us the answer. Aha! Yeah. Looky here. These look like burrows. These look like insect burrows. Not super convincing at first. We'll look around and see if we can find some more. These little circular vertical burrows. Let's see. Ha, ha, ha. Yeah. These look pretty good. Look at that one. These are pretty good. I think, by golly, we found some insect burrows in the floodplain deposits. Yeah, look at this. There's all kinds of horizontal burrows, and some of them even have meniscate backfilling. That's typical of cicadas, and some beetle larvae do that. So there's the burrow trace, and there's some faint meniscae. Here's another burrow trace. Here's another one. So they're there. Each of these knobs is a vertical burrow. There's some horizontal ones. This is extensively reworked by insects like beetles, cicadas, maybe some earthworms. So we're definitely out of the main channel, and we're on the forest floor. We're on the floodplain floor. And here's some more of these sinuous trails, typical of beetle grubs or even cicada nymphs do that. This one actually has natural cast in it, along with all the vertical burrows, the vertical holes. So different species of beetle larvae do different types of burrow morphology. Tiger beetles and June bugs and a variety of others make these vertical burrows, escape burrows. Horizontal ones could be like, say, cicada nymphs or beetle larvae kind of moving through the sediment. Oh, look at this one. There is some meniscae. You can see little packages of sediment that were left behind as the beetle moved, or the animal, might have been a cicada. So it's going that way, backfilling as it went. Okay. Oh yeah, look at this. Those are some nice burrows. That's a good one. Here's some smaller ones. All kinds of, look at this, just gorgeous, gorgeous burrows in this sandstone. These bigger ones look a lot like either cicada nymph escape burrows when they're ready to mature and crawl out, or things like fig beetles make burrows like that. These smaller, straighter, cleaner ones look like tiger beetles, which make a dwelling chamber that's a very straight, somewhat sinuous, somewhat curved, but generally pretty straight and clean and narrow burrow like that. So typical overbank in a sandy soil system. This is just like my backyard in Texas, as a matter of fact. Okay, so we can say that this upper sandstone, this lighter color material, is overbank. This is not part of the main body of the channel. If it is, it's the very top of the bars of the channel after it's been abandoned. The fact that it's kind of splotchy and it's not really uniformly covering the entire channel body makes me think it's more like little splays or levees off of, if not this channel below us, the one that came after it and built on top of the channel body below us. It's got typical features of sandy overbank material in that it's got laminations, little ripples. Most importantly, it's got a lot of beetle burrows, and beetles love sandy soils that are well drained. They don't want to drown, so they tend to live in areas where the water table is pretty low. It fluctuates because when you get rain, it obviously rises high enough that you have plants and roots and all that kind of stuff. But it's down enough that these animals' burrows are not flooded permanently. They're not like crayfish or crabs where they want water in their burrow. They really don't want that. So they tend to live in pretty well-drained areas. So this upper sandstone is a well-drained, non-channel fill deposit outside of the channel, probably a splay or, like, say, a levee or something. So that's some information. Now we're going to get back into the channel body itself, which is below, and see if we can kind of figure out a little bit more about how it worked before it was abandoned and before this material came on top of it. As we walk along to the next stop on the cross-sectional view of the channel, it's worth pointing out that NASA has been really interested in these channels in particular because of their 3D exposure and the evidence of past life preserved in them. This is the perfect training ground for rovers, human astronauts, geologists that'll someday visit Mars and other planets, and the AI that's used by their machines. Wowee! This is gorgeous. A single giant dune, subaqueous dune, capped by that conglomerate. But look at the size of this dune. That's almost 2 meters tall. So you've got a significantly large dune building downstream, a single dune. Maybe it's a compound dune, but it looks like just a single, well, maybe I guess there's a couple of different dunes in there. But then it's capped by the conglomerate that comes over the top. So the conglomerate is, again, the last gasp of this channel, which is opposite what you usually expect. You usually expect the conglomerate to be at the base. So this is something where there was a final giant push of material before the channel was abandoned. Let's take a look at this compound dune. It actually turns out to be a little bit more complex now that I'm looking at it. So here's some gravel on the foresets. And you can see there's actually multiple scales of foresets making up a compound dune here on the top. When we get down, you can actually follow individual foresets the length of the dune. So it's, again, it's close to, it's 1.5 meters, 1.75 meters tall. It's definitely not a small dune. This is almost filling the entire channel depth before the gravel comes on. Yeah, this dune just keeps going. And in this case, it's actually sitting again on top of some conglomerate. So we've got these sandwiches of fine grain material, coarse grain material, fine grain material, of course. It's fairly chaotic. It's not really well organized. There does seem to be fine at the base, coarse grain, then fine, then coarse. But it seems pretty random, which probably reflects the randomness of the flows. Here's more of those downstream accreting slip faces of dunes. So again, we can actually see the channel bodies going that way. And sure enough, so are the foresets of the dunes indicating a flow that way. So we've got a lot of downstream accreting features. That tells us how this channel body filled. It wasn't meandering side to side. It wasn't filling with point bars and counterpoint bars or transverse bars. It was filling in with downstream accreting bars or just dunes. There's some indication these might be bars. It looks like there's big downstream accreting sets superimposed between the dunes, but that's kind of hard to tell from right here. So it might be a combination of downstream accreting bars and dunes. Okay, so we've been walking along the channel, going with the flow like a clast. It's a good way of going about life in general, just be a clast. I always tell my students that. What I want to do now is go back to the road because the road cuts right through the cross section. So we've had a lengthwise view of this body and it looks like everything's building downstream. There's no indication, it'd be kind of hard to spot in this orientation anyway, but there's not much of an indication of lateral accretion like point bars. Looks like everything's building downstream-ish. So we're going to go look at the cross-sectional view and see if that holds up to what we're seeing lengthwise. We already looked at the top surface. I think once we see that cross-section, we'll be able to make some good proclamations about what this channel body is and what it represents. Okay, so the light could be better. If I was here earlier in the summer when the sun was to the north, this would be lit up really nicely. But we can still see some pretty interesting features in this cut. And we're going to take a look at it right now and finalize our interpretation of this freaky channel body. Getting the sun behind the rock was super helpful. This is a much cleaner expression of the full succession of the channel body, but most importantly, the floodplain material below it. This is a key to explaining why the channel is sitting by itself in the middle of this wasteland. Kind of expect Mad Max to come riding over the hillside somewhere. It might yet happen, the day is young. That floodplain material you can see is very, very erodable. It's siltstone, it's claystone. In fact, we can do the taste test. I'm always telling you guys the best way to test the grain size is just go ahead and chew it. Oh man, that's creamy. Only a little bit of grit. That's a silty claystone. So this green material is chlorite-rich clay, which explains why it's weathered, why it's left behind the channel body. All the material lateral to this channel got eroded by the processes that are creating the current landscape. The channel body itself has protected this clay from erosion. It's acting like a roof on top of the clay. If you live out west, it's a roof. I'm from Brooklyn, we call it a roof. So it's a roof sitting on top of the claystone, protecting it. Everywhere else, the clay has been eroded. That clay is the overbank material. That's the floodplain material that the channel incised and started filling. So getting back to our profile and interpretation, that's a claystone. Then on top of it, it looks like it's kind of patagenically modified clay. In fact, it looks like you can almost make out some roots or burrows. Look at that. That looks like a burrow. There's a lot of crayfish burrows in environments like that, and they do tend to look like this. So I would make the interpretation that that is the mature soil horizon. That is the immature soil horizon. The crayfish have burrowed into it. Possibly it was a little pond or a low spot on the floodplain. which makes sense because when the channel avulsed, when it jumped into a spot on the floodplain, it occupied a low. Channels preferentially occupy low spots. They're lazy. So they jumped into the low spot here with these beautiful crayfish burrows, buried the crayfish, and you can see there's a scour surface where the channel is. And the initial deposits of the channel are that fine-grained sandstone. So the initial flows were actually fairly fine-grained before whack, another flow with a high velocity and lots of carrying capacity, hauling gravel and bigger cobbles of sandstone. We saw those chunks of limestone. So you kind of get the sense that this channel started life sort of small and innocuous, low energy, and before long, things really picked up like crazy, and we saw all that stuff back there, coarse-grained material. Now this channel doesn't have any indication that it was meandering. There's no indication of big scroll bars, and when we look at the satellite image, it doesn't look like any of the typical meandering streams in the world today. It doesn't even look really like a braided stream. It looks like a very straight a single channel, straight to moderately sinuous, slightly sinuous. So it was cut, fill, maybe a couple of episodes of flooding, depositing more, and then it was abandoned. So it doesn't seem like a very long-lasting channel. And in terms of scale, we've got a real advantage here because we can just zoom out on Google Earth and take a look to the east, and there's the Green River. The modern Green River channel is almost exactly the same size and morphology as this Cretaceous channel. The key difference being that the Green River channel is incising and removing sediment, whereas the Cretaceous channel was actually building up sediment in the surrounding floodplain, and it's aggradational. But that's a topic for a totally different video. With the advent of Google Earth and Google Maps, there's a tremendous amount of freely available satellite imagery of modern depositional environments that we can compare to well-preserved outcrops like this one. So for example, let's take a look at this point bar or scroll bar in Holocene deposits of the modern Trinity River on the Gulf Coast of Texas. You can clearly see the lateral accretion sets that give this scroll bar its name. And if we take a look at the satellite imagery of the outcrop that we're standing on right now, lo and behold, you start to see similar landforms. And just by tracing out surfaces that we see that look convincingly depositional, various scroll bars start to appear in the deposits immediately underneath the exhumed channel that we're looking at. So that's telling us that there's two different styles of fluvial systems at work here. We've got the lower channel belt system composed of scroll bars and meander bars, and then this uppermost one is something different. So if I had to make an interpretation, and I told you I would, so I am, it's not a typical fluvial channel. It's actually one of these little extreme outwash events with the main fluvial system back to the west. It was further towards the mountains, and this represents a freak event, possibly related to tectonics, possibly related to an earthquake and a bunch of sediment getting released and dumped down the mountain, overwhelming the local fluvial systems to the west and causing them to elongate and shoot out this coarse-grained material to the east. All right, as always, I hope you enjoyed the video. I hope you learned a thing or two. Share it with your friends. Go ahead and subscribe to the channel if you're so inclined, and I will see you on the outcrop. Take care.